So, recording, great. Last day, I thought I could get through chapter 3 in just this week without typing them up, and then I realized that, no, I probably need to type them up. So I was trying to be a hero, but here we are. I had to type them up anyways. Oh well, shame on me. So there you are, chapter 3 notes. So what you'll notice is, and kind of why I was in a panic, is that we really covered the first 2 pages. And so I'm gonna try to get through the rest of the pages. I mean, there's only 6, so not a lot of explanations. So that's kind of what we're doing today. Okay. Next day, I'll give you 3.4. I'm not supposed to print on my own. I'm supposed to send it to the printers. So that's why I didn't do all the pages. I just did the ones we need for today, and then I'll give you another little booklet next day. Assignment 2 is in. Yeah, I know it's not a fun one. So make sure you get that in. Assignment 2 sucks. It's okay. You tried it. You did it. Right? We'll work on it for test 1, and then you'll just get better and better at it. Okay? So last day we talked about, or we introduced this idea of Z-scores. Right? Z-scores tell us how many standard deviations something is from the mean. Right? And so that's useful because then what we also said was, well, okay, here I tried to, I had to program this in R so you guys can appreciate how tricky that was, but pretty proud of it. So that's pretty good. Well, it doesn't look good. Looks fine. And so we said, okay, we've got this 68, 95, 99.7 rule, where if we're from the mean, let's say the mean is 0, and the standard deviation is 1 in this case, I have to make it simple, right? Then each tick is 1 standard deviation. Right? And so if we move out 1 standard deviation on either side of the mean, then we've covered the central 68% of the population. 2 standard deviations, we've covered the central 95%. And then 3 standard deviations, we've covered basically all words. C, 99.7%. So that's the 68, 95, 99.7 rule. Also called the empirical rule, but I like to just call it what it is. Save some thinking. Right? And so we can use these areas to find other probabilities. For example, I'm going to skip to I think page 2. This is what we went through last day. Oh yeah, so here's where we ended. So we developed this Z-score formula. Right? Z is x minus mu over sigma. We'll zoom in here. And we kind of said, well, if we had to just think it through, what we would do is we would find the distance, right? And then divide it by the standard deviation. And that's all the Z-score is doing. It's finding the distance between x and mu, and then dividing by the standard deviation. Right? So it's telling you how many standard deviations x is from the mean. And that's going to be really important from here on out. Okay? That kind of idea that a Z-score tells us how far x is from the mean, right, in standard deviations. So then we developed this Z-score, right? We got this negative here, and what we said was, well, any Z-score that's negative, it's just saying that this value is below the mean, right? And a positive Z-score is above the mean. Okay. So here's kind of our new stuff on page 3. So z-scores, we call them that they're standardized values, right? And so even if you're pulling something from a distribution where the mean is 4 and the standard deviation is 3, and then you pull another thing where the mean is 30 and the standard deviation is 20, right? You're still able to standardize those, and you're able to compare values from those two populations, even though they have different means and standard deviations. Because we can just talk in terms of, whoops, how many standard deviations something is from the mean, regardless of what it is. Okay. So z-scores will follow a z distribution, right? And so the distribution of z is a special case. Okay? So it follows a normal distribution. Okay? It has a mean of 0. And it has a standard deviation of 1. Okay? So really what I drew in my 68, 95, 99.7 rule was really the z distribution. Right? Just shrunk it down, centered it on 0 with a standard deviation of 1. Thank you. Okay. So I guess I'll put the date on here. What is the date on today? 30th. Oh my goodness. So this information, right, just like before when we had those probability rules that we summarized on the formula sheet, right, as P of A is between 0 and 1, right, those rules, same thing. We can summarize these rules about Z follows a normal distribution with a mean of 0 and a standard deviation of 1. And we use this notation here. And then you read this tilde as follows and we use this notation for whenever we're talking about distributions. So follows and then the n says a normal distribution. And we'll look at the binomial distribution as well, so it'll have kind of the same setup. But for now, we're just talking about the normal distribution with a mean of 0 and a standard deviation of 1. So in general, we can use this notation n mu sigma just as shorthand for Z follows a normal distribution with a mean of 0 and a standard deviation of 1. Right? That's just condensed into this notation. Okay. So, and I have that on here. So, you read that Z follows, that's the tilde. Normal distribution with a mean of 0 and a standard deviation of 1. The reason I'm kind of harping on it is because a lot of the time I see people trying to plug in a value for n, right, in here, which kind of makes sense, right? Because lowercase n is your sample size, so fair enough. Right? But here, this n is just denoting the normal distribution, right, with a mean and a standard deviation. So in general, right, any value of x, if it follows a normal distribution with a mean mu and a standard deviation sigma, this is how we denote it. Put a little link here to the follows, that's the tilde. People tend to not like that one very much. Should I turn some lights out here? Try to, or is it okay back there? Oh, yes. I usually hear that, but, well, now I do. A little hard hearing. So, yeah, that's much better. So, what we can do right? Knowing the Z distribution, now we can revise the 68, 95, 99.7 rule and make it a little bit simpler for Zs, right? And say that, okay, well, a Z, right, the area between a Z of -1 and 1, right? So -1 and 1, that is 1 standard deviation away, right, from 0, because Z is centered on 0 with a standard deviation of 1. So you've moved out 1 standard deviation on either side. And so it becomes a little bit simpler, right, but the idea is the same. So captures a central 90 or 68% of the curve. Between Z of -2 and 2, 95, -3 and 3, 99.7. Right? So it just kind of smushes it down a little bit. Any questions so far? Yeah. So as I was kind of warning you, I guess, last day, is that we don't use the 68, 95, 99.7 rule always, right? We might want more precise values, and that's where the Z table comes in. And so if you don't have a table with you today, you can, well, if you don't have one, you can grab one. Otherwise, you can just borrow them. But anyways, in about 2 minutes, you'll need it. Does anyone need a copy? If you didn't get a chapter 3 handout, you can grab one at the front. No, it's okay. Guess I should check in. Handout, formula sheet. Great. Okay. Oh. Yeah, you got it. Okay. So let's look at this example. So what's the probability of an observation being less than 3.4 if the mean is 5.3 and the standard deviation is 1.2? Right, so I'm giving you an observation. That's going to be our x. Okay. And so here, just making little notes here, this will be our x. The mean is mu, right? And the standard deviation is sigma. We said, okay, well, here, kind of tricky, right? Because we want to know what the probability is. We established last day that the probability is the area under the curve, right? So we want to be able to use the areas under the curve, right? But all we have is this observation, the mean, and the standard deviation. Okay, so what we do is, first thing you're going to do, right, is you're going to calculate your Z score. Right? Z tells you how many standard deviations you are away from the mean. And then, once you have your Z score, we could look at this and say, okay, well, wherever it falls in here, we could map out and approximate the area that we want. Okay. So what this is going to look like, I guess I must have been on a roll yesterday. It was earlier in the day, clearly, I don't remember. Well, now I do, but. Right. And so here, we have this distribution, and we want to know what is the probability of an observation being less than this value? Right? And so the probability that we want, right, is going to be this area here. Got messy in there. So what you're going to want to do is you're going to want to draw your normal distribution for these questions, because that's a good jumping off point, right? And just kind of figure out what information you have. Okay. So here, for us, if we just had to draw it by hand, we would draw our normal distribution, and it would be centered on 5.3, and then I would just jot down the sigma as 1.2, somewhere. It doesn't really go on the graph, I just kind of put it there so I have the information. And then I want to know something about 3.4. Well, this here is a number line, right? So whatever we're talking about, this is just on a number line here. So 3.4 is going to go somewhere below it. And it's actually not important where you put it, because we're just doing it to visualize things. Okay? So you don't have to put a lot of thought into where you put it. In fact, I always tend to put, if it's below, I tend to put it kind of somewhere here in the middle so it's easy to see, right? Even if I think it's really close, I'm not going to draw it really close there because then it's hard to see. So we draw this curve just to visualize things and kind of map out what we need. And so here, I'll do a better job of shading it in. That area under the curve, that's the probability that we want. Okay. So we can calculate our z-score. I have it here, but 3.4 is our x. I'll jot it down right beside. It's nice to just do it, especially because it's among our first times. All right, so z is x minus mu over sigma. That's on your formula sheet. Okay. So z is going to be 3.4 minus 5.3. Finding the distance between 3.4 and 5.3, divided by the sigma, which is 1.2, which is roughly 1.583. Actually, it's equal to 1.5833 repeating. I said approximately equal in the typed out ones. I'm a stickler for that kind of stuff, I guess. Not if you guys do it, but for me, it's not equal to, it's approximately equal to. Okay. So what we could say is, okay, this was our original curve, right? Our original normal distribution, but now we know that 3.4 translates to negative 1.583 repeating. 5.3, you shimmy it down, right? Z is centered on 0. 5.3 is 0 standard deviations away from 5.3, so fair enough, right? And then our standard deviation is now 1. So we can redraw this curve. Use a slightly different color here. And say that, well, our Z curve is going to look the same, but centered on 0 with a standard deviation of 1. And this value is at negative 1.583 repeating. But this is still the area that we want. And this area is the same as the area we drew before, right? We've just kind of well, we've standardized it down to this z-score. So what we could do, we could just keep using the 68, 95, 99.7 rule. Because we could say, well, if this is the area that we want, right, then I know the area in the tail from -1, and I know the area in the tail from -2. Right. Draw those on. I could say, well, somewhere here is -1, and somewhere here is -2. Right? -1.583 is somewhere between those two values. From the 68, 95, 99.7 rule, what we could show is that the area in the tail from -1, well, if we imagine here at 1, we've got 68 between those 2 points, and then we've got 32 left over. Split those in half, right? This area is 0.16. Right? So you can use the 68, 95, 99.7 rule to break up all these pieces and get all kinds of information, and you can just add up those areas, right? Subtract areas that you don't want. And same thing for the -2 area on this side is going to be, well, between 2 and -2, you've got 95%, right? Means you have 5% left over, but has to be split evenly amongst the tails, right? Because it's symmetric. And so we have 2.5% or 0.025 in this tail. If you ask me, this is a perfectly good way to do things, because then you would just use some software to figure out the actual area in the tail. Okay? But I think it's pretty human to think, well, so the probability is somewhere between 0.025 and 0.16. That doesn't help me at all, right? And so we want these more precise values, right? Because this range is way too big, right, for us to handle, I guess. We don't like it, right? But as long as you can convince yourself that this area, right, is going to be between this area, right? It's less than 0.16, but it's also larger than 0.025. And so you could use the 68, 95, 99.7 rule that way. But what we're going to do is we're going to use the Z table instead. Okay. So the Z table is basically like the 68, 95, 99.7 rule, except it goes by increments of, well, it shows 2 decimal places. So what is that, hundredths? Tenths? Hundredths? Doesn't matter. Anyways, so all it's done is so we're on the Z table here. That's table A. In fact, looks like this. Okay. Easier to just show you on here. So all it's done is it started at a Z of -3.4, -3.3, -3.2, blah, 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 blah. But it didn't stop there. It said, well, you must want a second decimal place. Right? And so what we do is you find your whole number in the first decimal in this margin, the left-hand margin. And then you find your second decimal in the top row. So in our case, we have negative 1.5833333. We have to round to 2 decimal places because we're about to use this table that only has 2 decimal places, right? So you have to round your value properly, right? So use proper rounding, round it to 2 decimal places. And even if you haven't done it, when you get to the table, you'll see, oh, I need just 2 decimal places, or I can only have 2 decimal places, right? And so that'll be your cue to round it properly. So here, negative 1.5, that's our first chunk, right? So we find that value here. And then we had negative 1.58 for our z-score. Right? And so 8 is over here, so we join them up. Cross-head looking at this, there. So on your table, you should find 0.0571. So what it's telling you is the area to the left, and that's what this little note at the top is saying. These values are only the areas to the left. But just like the complement, right? We could find the area to the right. If we know the area to the left, we know the area to the right because we know the total area is 1, right? And so that's why they only bother doing one side, right, the left-hand side. And you'll notice if you flip over, right, so if you scroll down, if you look at this first page, right, these z's are all negative, right, so these are all below the mean. Okay. And then you flip to the next page, and here, all your z's are positive, right, so here's all your positive z's. So you want to be careful, do you have a positive or a negative z-score? Right? Because that'll tell you which side you should be on. Again, this only gives you areas to the left. Right? So of course, as we start here at a z of 0, 0, the area to the left is 0.5, which we know already, right? Because it's symmetric and centered on 0, right? So we've got 50% below it, 50% above it, right? And so these values are all just bigger than 0.5, right? And all it's doing is it's moving tiny, tiny increments every time and telling you the area to the left, telling you the area to the left. And we could use calculus to find these areas. We're not going to, right? That's why we have the tables, right? But that's also why these tables came about, because it's very tedious to calculate all these integrals all the time. And so someone said, oh, you know what? I'm just going to write a table. You guys can all use it. Right? So that's what's going on, just finding the areas under the curve. So the probability that we find, right? So these are all the probabilities in the, I call this the body of the table. Right? So you've got your z-scores, and then you've got the body of the table. And these are all your probabilities. So 0.0571 feels a lot more satisfying, right, than somewhere between 0.025 and 0.16, right? But notice 0.0571 is between 0.025 and 0.16. It's just, we've narrowed it down quite a bit. Okay. Any questions about that? So here, I wrote out the steps to using this table and also what we did in our example. So we're going to round our z to 2 decimal places, and that's going to be important. We have to match the number of decimal places in the table. Maybe I'll make a note of it. Need to match the number of decimal places in the table. So now what we found, if we draw out our curve, all centered on 0, negative 1.58, this area is 0.0571. Or sometimes what I like to do is just kind of draw an arrow saying, oh, this area, 0.0571. Just like before, and it's not something I want you to worry about or anything, but I do want to show you how you would do it in R as well, right, just to make that link. And so you can use a p-norm command, which I think I show you in lab 3. It takes x, mu, and sigma, and then it spits out the probability, so the area to the left. So just like the table, it only gives the area to the left, but you can use that to find the area to the right. So I'll just make a note here. This is x, this is mu, and this is sigma. Notice that this answer is slightly different, right? But that's because we had to round our z-score, right? We had to round it to 2 decimal places, but it's really negative 1.583 repeating, and so R is able to handle that. So this is what I mean by, we could probably do away with the tables and just have something like this instead, finding our areas. Okay. Of course, on the test, you'll have to know how to use the Z table because you're not going to have a computer, unfortunately. Okay. Here's a note that always throws people off. What if you get a z-score of, well, let's take the one that we had earlier, negative 5.455, right? Negative 5 something. Okay. If you try to find that on your table, you'll see that, okay, well, on the left-hand side, these are all decreasing, right? Getting closer and closer to 0. And so our largest negative value seems to be negative 3.49, right? And it's going to be the same thing on the positive side. If you try to max out your z-score on the positive side, it's also going to be, so starting at 0, moving out, 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 right? Starting at 0, it moves out, 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 out. 3.49. So if you have a value that's beyond 3.49, right, plus or minus, what we could say is, well, we could say, well, technically, going back to negative 3.49, technically, the area in the tail, if it's beyond negative 3.49, is less than, right, it would just be less than 0.0002. That's really small. And so what I'm going to do and encourage you to do is just say, it's approximately 0. Right? And so it's important that you don't say that it is 0, because there's always a probability of things happening. Remember, those tails never close. Okay? And so there's always a probability of something happening. And so it would be wrong if you said the probability is 0. The probability is approximately 0. That's safe. Right? But you can't say it is 0. You can say it's less than 0.0002, right? Or approximately 0. And I think I did say that It's very important. Don't say the probability is 0. There's always a probability of something happening. Right? We have to keep that in mind. And so I have this here. So whenever you're kind of beyond the table, right, then technically the area is less than 0.0002. Okay? Or if we had to draw it, centered on 0, right? Because we're talking z-scores. Z-scores follow a normal distribution centered on 0. And here at negative 3.49 and positive 3.49, the area in the tail here is 0.002. 0.0002. Okay. Here's where that symmetry thing comes into play. Right. This value is the same distance from the mean as this value, right? And because it's symmetric, this area in the tail will be the same as this area in the tail. Right? And so even if you need the area in the tail of a positive one, you could use the trick of finding it for the negative and then just applying it to the positive side. Okay? The reason is, so here, what you would find in the table is the area to the left of 3.49 is 0.9998. Right? To find the area in the tail, 1 minus 0.9998, 0.0002. So once you're out far enough into the tails, the area to the left is going to be approximately 0. Also, if you're out far in the tails, right, the area to the right is approximately 1. Same idea. As long as you say approximately, you're safe. Good. Any questions? Okay. So, what we can do, right, and what we just kind of did, we'll do an example, is we're given some value and we want to find the probability associated with it, right? So what we have is we had some x that we turned into a z to find a probability, right? So we started with an x, we want a probability. Okay. Z's kind of the gateway. Okay. So we got from x to z by using z is x minus mu over sigma. And we got from z to a probability using the z table. So you have to keep in mind that it's a two-step process. Another way that we could ask questions is, well, what value is cutting off the top 25%, for example, right? Or the lowest 10%. So now I'm giving you a probability and I'm asking you to find the value, right? So you would go through the same motions but backwards. Right? And so I call it working backwards, just because in my mind here we're working forwards and then we can work backwards, right? But it goes either way. So you have to start at one of the endpoints and move your way to the other side. So let's do an example. See what's going on here. This is kind of a typical problem. So I think we know if you go to the vending machine and your bag of chips says it weighs some amount, I think we all know that it doesn't weigh exactly that amount, right? We know that there's going to be variation between the weights, right? But we are expecting it to be around that weight, right? And so those weights would follow a normal distribution, right? And so here, a cereal manufacturer has a machine that fills the boxes, no doubt. Boxes are labeled 16 ounces. So weird, because I stole this from a Canadian textbook, but they're still using ounces, and I didn't do the conversion. So anyways, so the company wants to have that much cereal in each box, of course, right? They understand that every time they fill it, it's not going to fill it with exactly 16 ounces, right? So if the machine is set at exactly 16 ounces, right, trying to fill to 16 ounces, it's going to underfill it half of the time, right? Just because 16 would be in the middle, right? You don't want that. So you try to fill it a little bit more, right? So you set it to set or to fill to, oh, and then there's this warning. Then about half the boxes will be underweight, making consumers unhappy and exposing the company to bad publicity and possible lawsuits. Dun, dun, dun. To prevent underweight boxes, the manufacturer has set the mean a little higher than 16 ounces, of course. So you want to shift that where it's filling to, right, so that you're not constantly getting all these underweight boxes, constantly, half the time. So based on their experience with the machine, the company believes the amount of cereal in a box fits a normal distribution with a standard deviation of 0.2 ounces. Okay. And so based off of that, the manufacturer decides to set the machine to put an average of 16.3 ounces in each box. Right. So the machine is set to fill at 16.3, but we also know that the standard deviation, right, the wiggle room is going to be 0.2. Okay. So here, we're told that mu is 16.3 and sigma is 0.2. Oh. And I left you the page, but you might need more paper. So A asks, what proportion of the boxes will be underweight? Okay. So we said 16, anything less than 16, that's underweight. Right? So these problems, sometimes you have to kind of think about, well, what does it mean to be underweight? What value am I looking for? Right? And so if we start by drawing our normal distribution, centered on 16.3, because it's centered on mu, and sigma is 0.2, 16 would be somewhere below it, right? So I'm not going to be too careful about it, just put 16 here, and this is underweight. So this area here is the probability of finding a box that's underweight, right? If it's set to fill at 16.3 with a standard deviation of 0.2. The question asks for what proportion. Okay. We've already kind of talked about this, but a proportion is a probability, which is basically a percentage. Right? So you have to keep those in mind. All those three P's, they mean the same thing. So regardless of which one I use, I'm looking for the area under the curve. Right? And so what proportion of boxes will be underweight? I'm looking for this area here. Right? Okay. So we have our 16, that's our x. Right? Your x is always going to be the value that's cutting off the region that you want, right? So your x is the one that kind of moves around all the time, right? Your mu stays steady in the center, and your sigma just is sigma. People don't tend to mess up or mix up sigma and mu. It's the x and the mu, keeping those straight, right? But as long as you remember that x is the one that moves around, and it's the one that we're interested in, right? Mu just stays in the middle. Thanks. Oops. So we want to find this area, right? This probability or proportion. And so we've gone next, we want a probability. We have to convert to a z-score first, right? And so our z is x minus mu over sigma. Our x in this case is 16 minus 16.3 over 0.2. Probably, but I don't try to be a hero about this stuff. 16 minus 16.3 divided by 0.2, negative 1.5. I'm going to put a 0 on there, right? Because we know we need 2 decimal places. So the second decimal place would just be 0. That's kind of our first step. Just to save myself a little bit of space, I'll put a second step, the second step beside it. Usually I like to work down a page, but real estate is at a premium here. So now what I'm going to do is I'm just going to write out what I'm doing, right? And I encourage you to do the same thing, because there's a lot of ways that you could write this down and it be inaccurate. Right? And so using the Z table, that's what I'm doing. We find the area to the left of Z equal to negative 1.50 is negative 1.5. So the whole number in the first decimal is in the left-hand margin. And then join it up with a second decimal of 0. You've got 0.0668 is 0.0668. Because that's the area that we're looking for, that's the answer. You would start there, even if I wanted to know, well, what proportion of boxes are not underweight? That would be 1 minus 0.0668, right? But because your first stop is finding the area to the left, I'm going to write that out. And so, therefore, the proportion of underweight boxes is 0.0668. Here's something that I see a lot, and I don't want to see it. I do this warning every day, every year, every term. Z is equal to negative 1.50, which is equal to 0.0668. That's never true. Negative 1.5 is never equal to 0.0668, right? And so I don't want to see equal signs being of use. Right? If you don't want to write out this blur, it's the safest, right? But if you don't want to write it out, you can use probability notation. Those are your two options, okay? Because otherwise, I end up seeing a lot of stuff like this, or just 0.0668 is somewhere kind of jotted down. And yeah, of course, I know what you mean. Of course, I've seen this work, I don't know, probably thousands of times now. I know what you mean, but it's not, you're not saying what you think you're saying, right? And so it's important that you kind of establish, but even if you use this sentence over and over and over again, that's fine, right? That's what I'll do. I just always use a sentence because a lot of people don't like probability notation, right? So instead of writing this, this can be replaced by the probability that Z is less than or equal to negative 1.50 is 0.0668. I think we can all agree that that's a lot shorter, right? But you do have to keep track of your probability notation. On the plus side, it'll always have this structure, right? The probability that Z is less than or equal to whatever Z you gave it is the number in the table. Right? So that's fine. But for my examples, I'll use the word version, right? Because it's also explaining what I'm doing. Okay? Using the Z table, we find the area to the left of Z equal to negative 1.5 is 0.0668. Wordy, but gets the job done. So you've got options, this or this. I don't want to see any rogue equal signs. It's not true. Okay. Any questions about that one? No? So let's keep going. Part B. What proportion of boxes weigh more than 17.21 ounces? Okay. So now we want to know, well, you know what? I'm going to insert, add page. Nice. I'll just do it here. Part B. You'll notice I always start by drawing out the normal distribution, because it gives me a kind of a map of what I need to do, right? What I know and what I need to do. So it was centered on 16.3 and sigma is still 0.2, but now we're interested in something like 17.21. Again, even though I suspect it's probably further out in the tail, I'm just drawing it here kind of in the middle, just so I can look at it and say, oh, well, this is the area that I want, right? What proportion of boxes weigh more than this value? So this is the area that we want. Okay. Same steps. Step 1. Find your Z score. Z is x minus mu over sigma. Oops. Mix them up. 17.21 minus 16.3 over 0.2. Oops. 17.21 minus 16.3 divided by 0.2. Oops. Should write out my
0.91 divided by 0.2. You don't have to, but it's just so you can check your work. I get 4.55. So here I'm just illustrating a situation where we're off the table, right? And so all we know, well, we can draw out a z-score distribution centered on 0. Here, we're way out in the tail, 4.55. We know from the z table that the area in the tail from 3.49, not 5, is 0.0002. So all we can say is, well, we've got those two options, right? We can say, well, it's just less than 0.0002, or as soon as we get something larger, right, on either end, larger than 3.49, we can just say, oh, the area in the tail is approximately 0. I'll write out the wordy version using the Z table. So it's step 2. We find the maximum Z score is Z equal to 3.49. With an area to the left of 0.9998. So the area to the right is 1 minus 0.998. Oops, sneak another 9 in there. Therefore, the area to the right of Z equal to 4.55 is less than 0.0002. Oof. Or we could just say the area in the tail is approximately 0. The area in the tail is approximately 0. Or probability notation, the probability that Z is greater than, yeah. I was gonna see if I should use the same structure. No, it's just easier this way. The probability that Z is greater than or equal to 4.55 is less than 0.0002. Yes. You're allowed to do squiggly equals, but no straight equals, because 0.0002 is not equal to 0. It's approximately equal to 0. Good. So that's just an example of going off the table. What do? It actually makes things easier, right? Because you don't have to write out that huge blurb. You could just jump the gun and say, well, the area in the tail is approximately 0. If you think about this, right? we were finding the probability of a box weighing more than 17.21 ounces. Right? What's the probability of a box weighing less than 17.21 ounces? Approximately 1, right? Because if you're moving out in the area and the tail is approximately 0, then the area below it must be approximately 1. Need another page, I guess. Okay. C. What proportion of boxes will weigh between 16.11 ounces and 16.61 ounces? Okay. So now, C, if we draw this out, we're still centered on 16.3. Oops. Was it 1.1? And 16.61. Just jot down sigma somewhere. 0.2. So now we want to know, okay, well, what proportion of boxes weigh between these two weights? So the area that we're looking for is this area here. So what we can do, right, as long as we think of these as puzzle pieces, there's lots of ways that we could do it. We could say, well, I know the total area is 1, right? And the area that I want is just basically removing those two pieces, right? So one thing you could do is you could figure out the area and the tails for each of these values and subtract them from 1. And then you're left with the area that you want. My kind of go-to way of doing it, because the table, the Z table, gives you the area to the left, right? I just go in and I calculate the Z score for this little guy, find the area to the left here, and then do the same thing, calculate the Z score, find the area to the left of this little guy, and take it away, right? Because then I have this whole area minus this area. That's the area that I want. So there's lots of ways that you could do it. You could get weird about it and find this area, add it to this area. Not sure why that would be a lot more work than you have to do. What else could you do? Nothing else off the top of my head. But there's lots of ways that you could do it, and you would all get to the same answer. So that's fine, as long as you show me what you're doing. Right, what you're thinking, that's fine. Okay. So what we're gonna do is I'm just gonna call this lower and upper. Because what we're gonna do is we're gonna treat these independently, right? And so we're gonna find a Z score for the lower value and a Z score for the upper value. The reason I'm writing lower and upper, we could just do 16.11 and 16.61, but because I want you to have it, you know, just in general terms. So the first step is find Z upper, or lower if you want. So I just write a subscript upper, keep track of which one's which. You could do Z subscript 16.61, doesn't matter. So X minus mu over sigma. 16.61 minus 16.3 over 0.2. Is, oops, 0.31 over 0.2. Oops. We get 1.55. Nice, and 2 decimal places already. So here, you could go find the area to the left, right, just so you have it. 2. Using the Z table, we find the area to the left of Z equal to 1.55 is what? So now it's positive, so you have to go to the positive side, the sunny side of the sidewalk. 1.55, so 1.5, join it up with the 0.05, I get 0.9394. 0.9394. Great. So now we're going to do the same thing, find Z lower, is X minus mu over sigma. Which was 16.11 minus 16.3 over 0.2. Negative 0.19 over 0.2. Negative 0.95. Also, nicely, just 2 decimal places. Otherwise, we'd have to round it. So now, oops, step 4. Again, same blurb. Oh, for that second one, I'll just write the probability notation just so you have it. Just in case you prefer to use it, the probability that Z is less than or equal to 1.55 is 0.9394. So using the Z table, we find the area to the left of Z equal to negative 0.95 is, okay, so now, negative 0.9 is down at the bottom-ish. So negative 0.95 has an area to the left of 0.1711. Cool. Or if you prefer, the probability that Z is less than or equal to negative 0.95 is 0.1711. Need another page. So now, right, we can map these out. Step 5, let's call it. We can use the original centered on 16.3, but I think it's easier to just do it for z-scores. So 0, and then we've got negative 0.95 and positive, what was it, 1.55? So what we're told is that this area, oops, or what we found rather, is that this area was what was it, 9394. And then we were told that this area is 0.1711. The area between z equal to negative 0.95 and z equal to 1.55 is 0.9394 minus 0.1711, which is 0.9394 minus 0.1711, 0.7683. Just keeping in mind which area you want. This is the area that you want. So knowing that this whole chunk from here on down is 0.9394, and then we can just lob off 0.1711 and get the area that we want. Same way, right? If you prefer, right, if it makes more sense to you to find this area in the tail and then find this area in the tail, that would be 1 minus 0.9394, and then lob those tails off, that's fine. As long as you're telling me what you're doing, okay? So therefore, we can say, or in probability notation, the probability that z is between negative 0.95 and 1.55 is 0.9394 minus 0.1711, which is 0.7683. Nice. So usually we kind of talk in percentages, right? So the proportion of boxes that weigh between, what was it, 16.11 and 16.61 ounces, 76.83%, or 0.7683. Ooh. So that was some practice, just using z-scores to find probabilities. But like we said, we could be given a probability and have to find the x that corresponds to that probability. Right? And so part D, if they want to publish a guarantee such as no more than 4% of boxes weigh less than this value, right? What's that value going to be, right? So now we have this probability, right, or percentage, which is an area under the curve, and we have to find the x-score that corresponds to that area. And so part D, we started here. Still centered on 16.3 and sigma is still 0.2. Then at some point here, right, if they want to say no more than 4%, right? So this area has to be 4% or 0.04. Forcing that area to be 0.04. And then what is this area? So try that one, I guess over the weekend. And then we'll finish it next day. All right. Have a good weekend.